Hello friends, welcome back to our YouTube channel. If you like this video, please like, share and subscribe. I'll share our videos commanded by our experts, so let's begin.
If you like, please like, share and subscribe. So let's begin our today's topic. Let's begin.
Top developers at Anthropic and OpenAI are moving away from manual one-shot prompting. They're building self-contained, goal-driven loops functioning as autonomous software. In a traditional setup, you write a prompt, review the output, and manually move the data to its next destination.
This makes the human the primary bottleneck in the production chain. Loop engineering removes that bottleneck. You define a high-level goal, provide tool access, and set an exit condition. For now, the AI writes its own prompts, calls tools, and self-corrects until the goal is achieved. This process shows the operation line. Moving human effort away from writing clever prose
and toward building rigorous testing frameworks. However, removing the human bottleneck also removes the human safety net. This chart shows what happens when an exit condition is poorly defined. The system cannot recognize that it has failed. This creates an infinite loop. The AI traps itself in a cycle of failing and retrying without ever alerting you that anything is wrong. This is why the verify node and the sub-agent requirement are so important. If the primary agent reviews its own work, it is likely to overlook its own logic errors, leading to false positives. You have to build
separate, specialized
agents specifically to critique and find flaws in the primary agent output. Success requires pivoting to system design, managing complex contexts, and building testing frameworks.
While prompting isn't gone, single-shot commands are being replaced by systemic automation. The next stage of AI development is focused on infrastructure rather than the chat interface. Agentic loops are a high-leverage software architecture. Their utility depends entirely on strict human oversight and the quality of the guardrails you build around them. Top developers at firms like Anthropic and OpenAI are actively abandoning manual one-shot prompting. They are moving away from treating AI as a conversational chatbot and instead building it as a system of autonomous, goal-driven software. The structural limitation of manual prompting is that it imposes a strict bottleneck. It restricts AI output to a single conversational interaction, freezing the process until a human reviews the work. In this manual setup, the human carries the operational load, writing the prompt, receiving the answer, correcting the model's errors, and manually pasting the final output into a local file. To bypass this, engineering teams are replacing the chat interface with a framework known as loop engineering. Under this framework, the human developer's role shrinks to exactly 3 responsibilities: setting a high-level goal, providing the AI with tool access, and defining strict exit conditions. By removing continuous human intervention from the middle of the workflow, the system can execute complex, multi-step actions at a speed and scale that manual prompting cannot match. To understand how this transition works in practice, we need to look at the literal architecture required to build an automated loop. This diagram shows the starting point of the architecture. The entire process begins by establishing a static input from the developer. Notice how this goal feeds directly into a central autonomous processing environment, entirely bypassing the chat window. Inside this environment, the AI writes its own prompts, calls external tools, and evaluates its own progress in a continuous programmatic cycle. Because this cycle is self-directing, the developer must establish a required termination point. Without it, the system would process infinitely. We are going to deconstruct this continuous feedback pipeline to analyze exactly how an AI plans, acts, and self-corrects inside that central loop. Replacing open-ended chat interactions with a bounded architecture provides the control necessary to integrate AI reliably into heavy production software. We can map this architecture using a real-world case study, a coding pipeline built with tools like Claude Code, often called a ship-until-green workflow. The process starts with a specific goal provided by the human developer: fix a broken data script. Next, the system is granted access to specific tools. For this task, it receives branching permissions in the repository and access to the automated testing suites. This flowchart illustrates the internal mechanics of the loop, structured as a strict 5-node programmatic cycle. The cycle begins in its initial state, task analysis. The AI does not immediately generate code. It analyzes the assignment and sequences the logical steps required to resolve the broken script. It dictates a specific plan: read the broken code file, locate the precise error, and formulate a patch strategy. This programmatic sequencing gives the system a clear map of its intended actions, a necessary prerequisite before it can execute tools autonomously. With the sequence planned, the system moves to execution. The system triggers a granted tool to execute an action, spinning up a temporary code branch in the repository. It writes the necessary patch based on its earlier plan and deploys the new code into that temporary branch. Then it encounters a point of friction. The system runs the automated testing suite on its new branch, and the test fails. Instead of stopping to ask a developer for help, the system immediately transitions into the data collection phase. During this observe phase, the system programmatically captures the raw error codes and output logs generated by the failed test. The system routes these error logs directly back into the AI's context window, treating the exact failure data as a brand new prompt. By ingesting the error logs directly, the system removes the manual debugging bottleneck, allowing it to interpret and resolve errors without human intervention. The loop now enters the evaluation phase, where the system must judge the effectiveness of its own recent correction. In agentic systems, there is a strict architectural rule: never let the same agent review its own code. To prevent bias, the output goes to a separate, highly specialized subagent. This model exists exclusively to evaluate recent code against the original exit criteria. Based on the subagent's evaluation, the system makes a routing decision. If the subagent detects remaining errors, the repeat condition triggers. The loop cycles back, modifies the code, and pushes the patch again. The exit condition is only met when all integration checks are perfectly green. Once verified, the loop terminates and alerts the developer. Utilizing an independent subagent for verification acts as the primary safeguard against degraded code quality as the system loops autonomously. While these automated cycles provide high-speed execution, deploying them at scale introduces systemic financial and technical risks. The most immediate constraint is financial, caused by dramatic spikes in API usage. This line graph shows the cost disparity. The flat line is manual prompting. Because an automated loop continuously feeds massive contexts of data back into itself, it drastically multiplies the token burn rate, resulting in a compounding cost curve. Beyond the financial burn, developers face a primary technical constraint: unchecked failures. If the exit criteria or evaluation subagents are poorly written, the AI can become trapped. It will spin in an infinite, highly expensive cycle of minor, ineffective code tweaks. Because human oversight is removed from the iteration process, both the financial cost and the risk of quiet, cascading failures scale exponentially. To mitigate these systemic trade-offs, human developers must completely shift their focus. Writing clever prose and optimizing traditional text prompts are rapidly depreciating skills. The new competencies are system design, strict context management, and architecting robust testing frameworks. The future of development relies entirely on the precise boundaries we build to govern autonomous iteration.